What if the most intelligent alien on this planet never came from outer space? What if it has been living in our oceans for 300 million years, quietly watching, thinking, and outsmarting its environment? To recognize an advanced mind, we rely on a very strict biological formula. We assume that complex cognition requires a massive, centralized brain, driven by millions of years of social evolution and nurtured by careful parental guidance. We see these traits clearly in the vertebrate lineages that usually meet our criteria for high intelligence. Primates, dolphins, and crows all possess dense centralized brains, rigid social structures, and long lifespans that allow them to learn over decades. And then there is the octopus, an animal that possesses no bones, operates with zero social structure, receives absolutely no parental guidance, and will typically die of old age before its third birthday. Yet, in laboratory settings, this solitary, short-lived invertebrate consistently solves multi-step, child-proof medication bottles. Instead of repeating a memorized solution, the octopus adapts in real time. When researchers change the locking mechanisms, the animal methodically reasons through the novel sequence of grips, twists, and pulls. It can even recognize human faces. In aquariums, octopuses observe researchers wearing identical uniforms and distinguish between them as individuals. They will routinely ignore some people entirely, while aiming deliberate, targeted squirts of water directly at researchers they have learned to dislike. Finding this level of strategic thinking and individual recognition in a creature with such a fleeting, solitary lifespan suggests that our traditional scientific model for what constitutes a mind is missing a massive piece of the puzzle. This forces an immediate question. How does an animal execute complex strategic problem-solving without a massive, centralized processing center? Looking at this schematic of the octopus nervous system provides the answer. There is a central brain located right between the eyes for making high-level decisions, but running down the length of each arm are 8 additional semi-autonomous nerve clusters known as ganglia. Because of these clusters, each arm acts as a partially independent decision-maker. If an arm reaches into a dark crevice to search for food, it doesn't wait for step-by-step instructions from the central brain. It actively explores, processes data, and makes micro-decisions on its own, only sending a summarized result back to the main brain. This localized processing is paired with remarkable physical hardware. Each arm contains up to 200 independently controllable suckers. These suckers are lined with chemoreceptors, allowing the animal to simultaneously feel and chemically taste the environment right down to the molecular level. A human fingertip has a highly concentrated set of touch receptors, but it cannot taste the chemical makeup of a surface. The octopus is reading its environment in a combined tactile and chemical language far richer than anything vertebrate evolution or human robotics has ever produced. This 9-brained network is a revolutionary alternative to the centralized model. By allowing the arms to handle high-resolution tactile data locally, while the central brain manages overall strategy, the system achieves a level of environmental mastery that individual neural clusters couldn't reach on their own. This biological ingenuity extends directly to its skin. An octopus can alter its physical texture, pattern, and color to flawlessly match any background in under 200 milliseconds. Looking at this extreme close-up of the octopus eye reveals a baffling biological impossibility. The animal is completely colorblind. Its eyes contain only a single type of photoreceptor. Anatomically, it cannot distinguish between different wavelengths of light. Current research suggests the answer lies in a physical phenomenon called chromatic aberration. This diagram illustrates how biological lenses bend incoming light, causing different color wavelengths to focus at slightly staggered distances behind the lens. The octopus exploits this physics trick. It rapidly shifts its uniquely shaped pupil to physically measure those staggered focal distances, effectively extracting specific color information from a monochromatic visual system. It found a way to see color without the biological equipment required to see color. Overcoming your anatomical limitations in real time requires physical ingenuity. To understand exactly how advanced this intelligence is, we have to look at tool use. In strict scientific terms, true tool use requires an animal to select an object, transport it at a personal physical cost, and save it for a specific future purpose. In 2009, researchers in Indonesia filmed veined octopuses collecting discarded coconut shell halves from the ocean floor. The animals gathered the halves, carried them away, and reassembled them into a protective shelter at a completely different location. Carrying heavy shells awkwardly across open sand drains immense energy and provides no immediate safety benefit. It is a calculated, future-oriented investment of resources happening in an animal that will live for a maximum of 3 years. This evolutionary timeline shows that the cephalopod lineage and the vertebrate lineage split over 500 million years ago. Since that exact moment, these two lineages have faced completely different environmental pressures. They rely on opposite neural architectures and experience vastly different lifespans. Yet both branches independently arrived at the exact same cognitive milestones: individual recognition, complex problem-solving, and tool use. The octopus demonstrates that a complex mind is not a biological accident unique to vertebrates. Given enough environmental complexity and evolutionary time, intelligence is an inevitable destination, a universal solution discovered on this planet twice, independently.